Hi, in this video, we will learn how to solve the inverse problem by using Gauss elimination method. Before we continue, let's review some mathematical background about the matrix operation. First of all, we have a row vector where you can see the vector can be written in this format. And then we have a column vector and the vector can be written in this format. So you can see that the size for the row vector is 1 times n, and then the size for the column vector is n multiplied with 1. This is the format for the matrix, and you can see that the size is n multiplied n, where you have n row multiplied with m column. So capital A in bracket indicate the matrix, and then when we expand it, we obtain this component where you have element A11 to A1 until column m, A21 until A2m, and then you continue up to A n row 1 until A n row m column. You must write the element number here correctly. For example, if I write A13, it indicates the former number to be first row, and then the later column is 3. So which means the first row at the third column. So this is the element that you should write. If the size m times n, where you have the m equal to n, for example 4 times 4, so in this case we call the matrix as square matrix. On the other hand, when the size m less than n or n less than m, for example like 5 times 4 or 3 times 4, so in this case it's called non-square matrix. When you perform multiplication between two matrices, you should make sure the interior dimension here to be the same. If it is not the same, then you cannot perform the multiplication. So in this case, let's try with this example. So you have 3 rows multiplied with 2 columns. Here you have 2 rows, 2 columns. And then you see the interior dimension, they are the same. So these two parts can be cancelled. You obtain the final product to be 3 times 2. So this is the final output that you should have. To obtain this answer, so first of all, you take the first row, multiply with the column here. So 3 multiplied 5, you get 15, plus 1 multiplied 7, you get 7. So total is 22. With that, you obtain this element. Then you continue multiply 3, 1 with the second column here to obtain this result. And then followed by this row. If you multiply with first column, then you obtain 82. Second row multiply with second column here, you obtain 84. And if you continue with the last row, then you should be able to obtain this answer. In this case, we have the size of the matrix here 2 times 2. The size of the matrix here is 3 times 2. So you see the interior dimensions are not the same. So therefore, we cannot perform matrix multiplication. So if you multiply between them, you will obtain error. The inverse matrix is equal to 1 divided by determinant A, and then take the multiplication with the adjoint A, where the adjoint A is equal to transpose of the cofactor A, which means you need to perform the cofactor A and then you perform the transpose. For example, let's say you have a 2 times 2 square matrix A here. So in this case, we are going to find the inversion of it. The general formula to compute the determinant A is take the A11, cross the column and row corresponding to it, take the determinant for the remaining terms, and then you should be able to multiply it. Then continue with the second element in the first row, which is A12. So cross the row and column corresponding to A12 and take the determinant for the remaining term. So multiply this determinant with the A12. And you have the positive, negative sign in front of it. So this is the convention of the sign that we follow. For the first row, we are using plus, minus, and so on. For the second row, you have negative start first, followed by positive, negative, positive, and so on. To find the cofactor for matrix A, for the first element, cross the row and column corresponding to it, and take the determinant for the remaining term. Then you get the answer for the first element. For the second element, cross the row and column corresponding to it, and take the determinant for the remaining term. Then you should be able to obtain this result. By using the same approach, cross the row and column for this element, and you should be able to obtain determinant A12 for this. Then cross the row and column for the last element, you obtain the determinant A11, which is this answer. And then you apply the convention sign here. For 2D, you have positive, negative here, and then negative, positive at the second row. So this is the cofactor answer. Then you can obtain the adjoint of the matrix A by taking the transpose of cofactor. So this is your cofactor. Let's take the transpose. And when you take the transpose, the diagonal term should be remain. So you have this to be remain the same. Then you switch the element Aij to the Aji, and from the element Aji switch to Aij. So for example, this term here, you switch to this position, you obtain negative A2i here. And for this element, negative A12, you switch to top to be this element. So this is the adjoint answer. Please be careful. This symbol is indicating the determinant function and is not absolute function. For example, if you take determinant for 5, you obtain 5. Determinant of negative 5, you still obtain negative 5. Determinant of 2D, let's say 1, 2, 3, 4, you obtain 2 minus 12. So for absolute case, so if you take absolute 5, so let's change the symbol to be ABS to indicate the absolute. Then you get 5. So absolute negative 5, you obtain 5, where we change the negative into positive. And then if you take absolute matrix 1, 3, 4, 2, you will still obtain 1, 3, 4, 2. And if you have negative 3 here, the negative will change to positive by using the absolute function. So you can see in general, absolute is changing the negative into positive, and determinant can be computed by using this operation. By using this formula, then you should be able to obtain the inverse matrix A to be this answer. What happens when you take matrix A multiplied with the inverse matrix A? So let's try. So we multiply the row with the column here. 2 multiplied 0.6, you obtain 1.2. 1 multiplied negative 0.2, you obtain negative 0.2. So we continue with the second column. 2 multiplied negative 0.2, you obtain negative 0.4. 1 multiplied 0.4, you obtain 0.4. So from here you obtain 0 for this term. This one you obtain 1. And if you continue with this component, multiply with these two columns, you should be able to obtain 0, 1 here. So this is called the identity matrix. So if you take the multiplication between matrix A and the inverse matrix A, or you take the inverse matrix A with the matrix A, you should be able to obtain the identity matrix, where you have this format. And you can see that identity matrix has 1 at the diagonal component, 0 at the non-diagonal component. If this equation is valid, where left hand side is equal to the right hand side, then we can say the matrix A is non-singular. So we can continue to apply it to solve inverse problem. So let's say initially you have AX equal to B, and we want to find the X. So A and B are given. So in this case, to cancel the A here, we multiply with the inverse A. So on your left hand side, it becomes identity. And identity multiplied with the X, you obtain X. So with that, you can compute the unknown X to be inverse matrix A multiplied with B. In some cases, when you compute the inverse matrix A, this component here is very close to this component. So when you minus them, and then you should get near to 0. So if you take 1 divided by some number near to 0, this is approaching infinity. So if this is the case, when you take the multiplication between the matrix A and inverse matrix A, then you cannot obtain identity. So in this case, we call the matrix A to be singular. So singular matrix is bad, because when we take the inverse matrix A with the A, so this term is no longer equal to identity. Let's say we let it to be equal to, let's say, matrix C. So Cx equal to inverse matrix A multiplied with B. So in this case, we cannot find the unknown X by using this formula. So you should know that if your matrix A is singular, then you cannot find the unknown X by using this formula. We can use the same method to find the inverse matrix for size 3 times 3, 4 times 4, and so on, by using the same step we saw in the 2 times 2 matrix previously. For example, let's say we have a 3 times 3 matrix in this case. Then first of all, we determine the determinant matrix to be this item. Referring to the first row here, the conventional sign is positive, negative, positive. And then put the element A11, A12, and A13 inside. Then cross the first column, first row, you obtain the determinant A22, A23, and so on to be this component. Cross the first row and second column, you obtain the determinant for A21, A23, A31, and A33 to be this component. Lastly, to determine this element here, so you cross this row and this column, you obtain determinant for this component. So you can continue to find the adjoint, and adjoint is equal to cofactor A, and then you take the transpose. So cofactor A can be found by this formula, where you have in the first row positive, negative, positive, second row negative, positive, negative, third row positive, negative, positive. To obtain the first element here, you cross this and then you take the determinant to be this answer. To find the element in the second row first column, then you cross the second row first column, so you take the determinant for A12, A13, A32, and A33. So by using the same procedure, you should be able to obtain the cofactor matrix A. Let's say you get the answer for cofactor to be this, and then take the transpose to obtain the adjoint. So your adjoint will be 5, 2, 1 here is the diagonal, so it shouldn't change. So remain. 6, 4 here, it should switch. Negative 3 and 3, it should be switch. 6 and 7, switch. Then this is the answer for adjoint. So substitute it inside the formula and also the determinant, you should be able to obtain this formula. After you find the inverse matrix, then we can substitute it into this formula to obtain the unknown X. So this formula is only valid when your matrix A is non-singular. And you can check whether a matrix A is singular or non-singular by using this relationship. If this equation is valid, then the matrix A is non-singular. If you perform the augmentation between the matrix A and identity matrix, so the result will be this. Augmentation is very useful when we want to simplify our equation. So this is the normal equation, and we can change to matrix format like this. During the calculation, the X matrix here remain unchanged. Only the blue and red matrix here will change during the calculation. Therefore, we can take the augmentation between these two matrices and eliminate the X matrix. This will save our time in writing. Don't forget to draw the line here to indicate the left hand side matrix and the right hand side matrix. This is the symmetric matrix where you have Aij equal to Aji. For example, at the non-diagonal element, which is this region, you see A21 here is equal to 1 and is equal to A12 here. You have A31 equal to A13, which is equal to 2. And lastly, you have A32 here, which is equal to A23. Since Aij equal to Aji in all the elements, we can say it is a symmetric matrix. Diagonal matrix is the matrix where you have non-zero at the diagonal component, and you obtain 0 at the non-diagonal element. Identity matrix is diagonal matrix where you have 1 at the diagonal component. If you have non-zero at the top part here or at the bottom part here in a triangular shape, so these are called triangular matrix. So if you have non-zero at the top, it will be upper triangular matrix. At the bottom should be the lower triangular matrix. If you have non-zero at the diagonal component, and also you have non-zero near the diagonal component here, then we call it as band matrix. So the width of the band matrix in this case, maximum you have 3 elements. So this is called the bandwidth equal to 3. If you have band matrix with the bandwidth equal to 3, so in this case, we can also call it to be tridiagonal matrix.